Hi there. Welcome to Dean of Science. Today, we're going to talk about what coordination compounds are. We're going to talk about the basic rules for coordination compound nomenclature, and we're going to go over how to solve example nomenclature problems. Any and all documents that you see in this video are available for download for free in the description. And with that introduction out of the way, let's begin. Okay, so what exactly is a coordination compound? Coordination compounds consist of two, or rather three parts. The first part would be a complex ion, which is actually split up into two other parts. The first part would be the transition metal, as characterized by our periodic table, and the second part would be the ligands that surround the transition metal. Ligands are just neutral molecules or ions that have a lone pair that can be used to bind to our transition metal ion in question. Now, the other part of a coordination compound would be the counterions. Counterions are just anions or cations that are needed to produce a net charge of 0 for our coordination compound. So let's say we had a +2 charge for a complex ion. We need a -2 charge as a whole for our counterions to produce a net charge of 0. Now, transition metals are considered a Lewis acid because they are an electron pair acceptor. Ligands are considered a Lewis base because they're electron pair donors. When we have a Lewis acid reacting with a Lewis base, we have what we call a coordinate covalent bond. And that's what's happening in the complex ion. So now that we understand what coordination compounds are, let's talk for a second about ligand types. Ligands are often characterized based on how they interact with our metal ion. So for example, if I had a monodentate or a unidentate ligand, that means my ligand can form only one bond to my metal ion. Some examples would be H2O water, NH3 ammonia, or CN cyanide. However, if I have a bidentate ligand, that means my ligand can form two bonds to the metal ion. Some examples of bidentates would be C2O42- oxalate and C2H4NH22 ethylene diamine. These are fairly common and are abbreviated OX and EN respectively in the chemical formulas of complex ions. Polydentates can form more than two bonds to the metal ion. So, for example, we have HNCH2CH2NH22 diethylene trimine, abbreviated DETA. Another example would be C10H16N2O8 ethylene diamine tetraacetate, abbreviated EDTA. These are not as common as the bidentates, but are fairly common in the general scheme of things. Okay. So eventually we reach coordination compound nomenclature. These are called textbook nomenclature rules, mainly because I base them off of chemical principles by Zumdahl and DeCoste, but of course I tweak them a little bit so they're easier to understand. For the most part, I'm going to be using the same examples throughout this piece, so you can kind of see how it all builds up together. So, let's get started. Rule number 1. Name the compound in order from cation to anion. So, remember what I said earlier. Coordination compounds consist of a complex ion and counterions. Either of these could be cations or anions, so how this is going to play out is you think of it similar to ionic compounding. For example, in this case, COH2O6 would be our complex ion that's also a cation because of its positive charge, so we name it first. Br3 in this case would be your counterions, and they're also anions, so they're named second. Note that in this case Br3 is called bromide, similar to how it would look in ionic compounding. Another example. In this case, Na2 would be our counterions, and they're also cations due to their positive charge, so they're named first. PTCl4 would be our complex ion that's also an anion, so it's named second. Rule number 2. Name the ligands before the metal ion in complex ions. going back to what we said earlier, a complex ion consists of a transition metal and ligands. So when we order them in nomenclature form, we name the ligands first, and then the transition metal. For example, in the complex ion COH2O6, we can see that H2O is the ligand, and CO is the transition metal. So when we order them, we name the ligand first, in this case H2O, and then the transition metal cobalt. In the complex ion PtCl4, we can see that the transition metal platinum is surrounded by chloride ligands. So we name the chloride ligands first, and then the platinum transition metal. Rule number 3. If your ligand is an anion, you add an O suffix to its root name. If your ligand is neutral, you have a special molecular name that you use. So for example, in this case, H2O water is our neutral ligand, so we refer to a special list. As we can see in this list, H2O water is called aqua, so we just name it aqua. In this case, Cl chloride is our ligand, and it's also an anion, so we add an O suffix to its name, so it becomes chloro. Some more examples of O suffixes. Fluoride turns into fluoro, bromide to bromo, hydroxide into hydroxo, cyanide to cyano, oxalate into oxalato, ethylene diamine tetraacetate into ethylene diamine tetraacetato. Generally, suffixes with "ide" turn into "o", "ate" to "ato", "ite" to "ito". However, when you have linkage isomers that differ from their point of connection with our transition metal, you may have different names to distinguish between the isomers. So, for example, in nitrite, we have N as our linkage point to our transition metal, so we call it nitrito N, or just plain nitro. For the cases in which oxygen is attached to our transition metal, we call it nitrito O, or just nitrito. Rule number 4. When you're naming your simple ligands, you want to use prefixes to denote the quantity, how many ligands are surrounding your transition metal. So you would use the prefixes mono, di, tri, tetra, penta, hexa to denote the quantities of 1, 2, 3, 4, 5, and 6 respectively. Although it's important to note that mono is usually omitted because we don't want to make our words too long or superfluous. So as examples, let's look at this. COH2O6, H2O is our ligand, and there are 6 of them, so we call it hexaqua. In this case, PtCl4, chloride is our ligand, and there are 4 of them, so we call it tetrachloro. However, if our ligand is not simple and is actually rather complex, or if our ligands already contain prefixes, we're going to use a special method. Instead of using bi, tri, tetra, etc., we're going to use bis, tris, tetrachus, pentachus, and hexachus to denote the quantities of 2, 3, 4, 5, and 6 respectively. And we're going to enclose this complex ligand in parentheses. So, for example, ZnEn3, ethylene diamine, is actually pretty complex if you look at it. So what we do is again enclose in parentheses, as stated here, and use our special prefixes. So because there are 3 of them, we're going to call it tris, and enclose it in parentheses, tris ethylene diamine. Rule number 5. If you have more than one type of ligand, you should name your ligands alphabetically, just disregarding any quantity prefixes when you're ordering them. So, for example, in this case, we have NH3 ammonia, which is a ligand, and we have chloride, Cl, as a ligand as well. The name for NH3 ammonia is amine because it's neutral, and the name for chloride is chloro. Amine comes before chloro in the alphabet, so NH3 is named first, even though it has a prefix, penta, that would have put it after chloro. Rule number 6. Transition metal ions will typically just use the regular name found in the periodic table, shown here. For example, in COH2O6Br3, cobalt, the transition metal ion in this case, would just be called cobalt. Simple enough. However, if your complex ion, read your complex ion, not your transition metal. If your complex ion is negatively charged, meaning it's in the anion state, what you're going to do is you're going to add an additional suffix ate to your metal ion name. So for example, in Na2PtCl4, the complex ion PtCl4 is in the anion state. So what is that going to do? Well, we're going to take your platinum name base and you're going to add an ATE to it. So it turns into platinate. Now, to make things a bit more complex, if your complex ion is negatively charged, so it's in the anion state like above, and your metal ion has a Latin root, you're going to use both the Latin root and the suffix ate. So what do I mean by Latin root? Well, take this for example, K3FeCN6. If you look at the chemical symbol for iron, Fe, it doesn't actually represent its English name. Instead, it represents its Latin name. So here's just a list of Latin names that you should be able to memorize. In this case, Fe stands for ferrate. So that's what we're going to call it. It includes both the Latin root and the suffix ate. The other Latin names would be copper, Cu, cuprate, lead, Pb, plumbate, silver, Ag, argentate, gold, Au, aurate, and tin, Sn, stannate. Rule number 7. After you name your transition metal ion, you should enclose in parentheses its oxidation number as Roman numerals. Going back to what we said earlier, counterions are needed to produce an integer of 0 for coordination compounds when combined with complex ions. So, this example should be solvable if you have enough background in algebra and oxidation numbers. In this case, we have cobalt, our transition metal, having a question mark to represent its oxidation number. We have 6 H2O water molecules, each having a charge of 0 because it's neutral. And we have 3 bromide ions, with each bromide ion having a -1 charge. So we have -3 charge total for the bromides. And we have all this totaling up to a charge of 0 for a coordination compound. And with a little bit of algebra, we take the -3, put it onto the other side, and we see that the oxidation number for cobalt is +3. That explains why we call it hexaqua cobalt 3. Now, for this example, let's take a look at each individual part. Each sodium ion, Na, has a +1 charge, and since there are 2 of them, we have a +2 charge. For platinum, that's our transition metal that we're trying to find, so we're leaving that as a question mark. For the chloride ions, each one is going to have a -1 charge, and there are 4 of them, so we have a -4 charge total for the chlorides. The +2 plus the -4 would equal a -2. Take the -2, put it onto the other side, and we see that the oxidation number for platinum is +2, which explains why it's called tetrachloroplatinate 2. So for some people, learning a whole bunch of rules isn't exactly the best way to learn. For some people, perhaps a more systematic or step-based method is preferred. This is a method I use personally. If you want to memorize rules, that's okay. Use this, fine. Use a different method, okay too. Just stick to the one that you're most comfortable with. In this method, what I do is I break the problem down step by step and just isolate our solutions one by one. So this is my step-based method. Step number 1. You want to divide your compound into 2 sections, your complex ion and your counterions. You should be able to name the counterions. So remembering what we said earlier, coordination compounds are made up of a complex ion and a whole bunch of counterions. The complex ion might not be as easy to name immediately, but the counterions you should be able to name. So whether you have a counter anion or a counter cation, you should be able to name both fairly easy at the beginning of the problem. Step number 2, we want to divide our complex ion into transition metal and its ligands. So going back, our complex ion is made up of a transition metal and the ligands. You should be able to name them separately. So what we want to do first is isolate them mentally and recognize what they are so we can name them later. You can do this by drawing a, kind of like a chart and making a line dividing the ligands and the transition metal, like so. Step number 3. Now that we recognize which are the ligands and which are the transition metals, we should begin naming. So step 3, name the ligands alphabetically with correct naming if it's neutral, or add no suffix. So remembering our rules earlier. If your ligand is an anion, use a no suffix, like so. Or if your ligand is neutral, have a special molecular name, like so. And in this case, you should be able to name the ligands separately, away from the transition metals. Remember, of course, that if you have more than one ligand, to keep your ligands, at least their initial name, in alphabetical order. Now that we have our initial ligand name down, step 4 is just adding our prefixes for the ligand quantity, and just using parentheses and bistress tetrakiss if your ligand is complex, just following the rules earlier on how to name depending on the number of atoms that you have in your complex ion. So now that we're done naming our ligands, we begin naming our transition metal. So going back to our rules earlier, we just remember that transition metal ions typically just use their regular name found in the periodic table. So you just look it up. But remember the special rules in the case of the transition metal being in the anion state, like so. Then you have an ATE suffix. Or if it's in the anion state and it has a Latin name, then you use the Latin name and the ATE suffix. So step 5 is just naming the transition metal. As we continue naming our transition metal, we still have to find our oxidation number. So step 6 is finding the oxidation number of our transition metal using algebra and writing in parentheses as a Roman numeral. If you've been following along, you'll realize that we've actually named all the components in the coordination compound already. So all we have to do is step 7, which is naming the compound in order using our information provided. So for example, if our complex ion comes first, followed by a counter ion, what we'll do is remember that in a complex ion, the ligands will come first. And the ligands consist of the ligand prefixes, the ligand names, in alphabetical order, and an O suffix if necessary. After your ligands, you'll have your transition metal, which includes the transition metal name and the transition metal oxidation number in Roman numerals. Followed by the complex ion, you'll have a separate word, and that'll be for your counter ion, which will be named actually initially. So you'll have that figured out. Alternatively, in step 7, if you have a counter ion followed by a complex ion, it'll go a little bit differently because our transition metal is now in the anion state. So what we do now is we begin with the cation, which you should be able to name, followed by our complex ion. So we begin again with the ligand prefixes, the ligand names, and the O suffix. Those are the ligands. Then you have the transition metal. The transition metal, if it's Latin, should have its Latin name, otherwise it's normal. And because it's in its anion state, you have an ATE suffix. And then finally, you have your oxidation Roman numeral. Following all of these 7 steps, you should be able to name your coordination compound fairly easily, especially with a lot of practice. To see how all this works in action, let's try an example problem. In this case, we have Fe, En2, NO2, 2, 2, SO4. What we want to do first is we want to divide our compound into 2 sections. First, the complex ion and the counter ions. In this case, it's a counter anion, and we should be able to name the counter ions almost immediately. In this case, it's sulfate. So that's checked off. Next, we want to move on to our complex ion, which is split up into 2 parts, our transition metal and our ligands. Our ligands will obviously come first, so let's go ahead and do that. Our ligand names, if done alphabetically with correct naming, would be ethylene diamine, and NO2 would be nitro. So, ligand names done, then to ligand prefixes. In this case, it's bis, with parentheses because it's complex, it's 2, and di because it's 2. Next, we want to move on to the transition metal. Our transition metal in this case, it's just going to be iron because it's not in the anion state, and we want to do a little bit of algebra. So, because there are a couple, too many 2's over here, let's move the 2's over here so we can distribute them as a coefficient. So first, we have to recognize that our variable would be Fe iron, so I'll just leave that as a question mark for right now. Ethylenediamine is a neutral molecule, so that's going to be 0. NO2, well, that's going to be a -1 charge, and there are 2 of them. And the 2 over here will distribute over here. So now let's distribute this. 2 question marks. 2 times 2 times 0, 0. 2 times 2 times -1, -4. And then we just have the sulfate, which is -2. And so here are all of our values so far. -4 plus -2 is -6. Pull that over to the other side. That's +6. 2 question marks equals +6. Divide. You have our oxidation number as +3. So it's going to be called iron 3 with a Roman numeral. So, putting that all in order, this is what we have. Bis ethylenediamine dinitro with O, iron 3 sulfate. Bis ethylenediamine dinitro, iron 3 sulfate. So next example, K2, Ni, CN4. In this example, we still want to divide our compound into 2 sections, the complex ion and the counter ions. In this case, we have a counter cation, and it's potassium. Next, we want to divide our complex ion into its transition metal and its ligands. The ligands will come first, so let's do that. The ligands in this case would just be cyanide, so it's cyano. There are 4, so it's called tetra. Ligands are done. Next, we move on to the transition metal. The transition metal in this case is nickel because it's in the anion state. It's going to include an ATE suffix. And then we do a little bit of algebra. So following this, we just go by the charges. Potassium, +1 charge each, 2. And for cyanide, -1 charge, 4 of them. So that's -4 here, +2 here. That's -2, plus the nickel. Move the -2 onto this side. You have your nickel oxidation state as +2. So it's called nickel 8, 2. So putting this all together, what do we have? We have potassium, tetracyano, nickel 8, 2, potassium, tetracyano, nickel 8, 2. For this last example, let's look at CO, NH3, 4, Cl2, I. What we want to do first is divide our compound into 2 sections, our complex ion and the counter ions, which in this case our counter anion is iodide. And next we want to divide our complex ion into its transition metal and its ligands. Ligands will come first, so let's name that first. Our ligands are NH3, so that's amine, and Cl, so that's chloride, becomes chloro. And there are 4 of them, so it becomes tetraamine. 2 chlorides, so it becomes dichloro. The ligands are done. And finally, we move on to the transition metal. Our transition metal in this case is cobalt. And it's not in the anion state, so don't worry about that. It's just cobalt for its name. Next, we use a little bit of algebra. So, again, let's go with the charges. NH3, it's neutral, so that's going to be 0. 0 times 4 is 0. Chloride, it's going to be a -1 charge. There are 2 of them, so that's a -2 charge total. Iodide, that's a -1 charge, so -1 charge total. -2 plus -1, that's -3. -3 onto the other side becomes +3. Our oxidation state for cobalt is 3. So let's put it all together. Here we have tetraamine, dichloro, cobalt 3 iodide. Tetraamine dichloro cobalt 3 iodide. So with that, we're actually done. Sorry that took so long. I think around 30 minutes or so, but I hope it was in depth. I hope it was useful. And if you need any of these documents in PDF form, I'll upload a link with them to the description bar. I hope you were able to learn, a little bit of coordination compounds. And that'll be all. This is Dean of Science, signing off.